In an unstructured procedural application, every line of code is potentially exposed to every other line. Changing a single attribute to fix a minor bug can trigger a domino effect of crashes as interconnected functions fail across the entire script. Senior developers avoid this chaos by building software as a collection of organized, independent modules. This architectural approach ensures that massive platforms remain stable even as they grow in complexity. We will use this professional methodology to build a fully functional, scalable mini banking system from the ground up in the next 5 minutes. If you have a basic understanding of variables and functions, you have the necessary foundation to follow along in your own code editor. This structured framework provides the tools to move beyond writing functional scripts and start engineering maintainable, resilient systems. Our project begins by defining a base account class. This serves as the primary blueprint for every financial record in our banking system. We implement encapsulation using a private access modifier. This hides the internal balance from outside functions, ensuring modification only by rules defined within the class. External logic cannot bypass these boundaries, preventing malicious attempts to set a negative balance. To expand without duplicating code, we use inheritance to create specialized classes. We create a savings account that derives its properties from the parent account class. It automatically gains all the security and functionality we've already built. By establishing these secure boundaries and hierarchical relationships, we create a resilient foundation that prioritizes code reuse. Polymorphism provides our system with flexibility. It allows different account types to respond to the same command in their own unique ways. If we issue an apply interest command, the standard account and the savings account will process different results based on their internal logic, despite receiving the same instruction. To manage the increasing complexity of these operations, we use abstraction. This principle focuses on what an object does rather than the specific details. We implement an abstract transaction class, hiding the complex data pathways behind a simple, high-level interface that only reveals essential triggers. Together, these 4 pillars act as the structural contracts of the system, turning individual instructions into a cohesive, manageable machine. As a system grows, even object-oriented code can become unmanageable if it isn't governed by strict design principles. The single responsibility principle dictates that each class should have only one reason to change. We have to ask, should our core account class be responsible for both managing funds and printing receipts? We refactor the code by splitting the responsibilities, moving all receipt logic into a dedicated printer class to ensure each module remains focused. The open-closed principle allows adding new functionality safely. When we add a business account module, it plugs directly into our hierarchy, while the original base classes remain locked and unchanged. Liskov substitution confirms that this new module can replace the parent account in our application logic without causing any errors or unexpected behavior. Enforcing these rules keeps the core architecture stable, even as the system grows and new features are added. Interface segregation prevents us from forcing client applications to rely on large, bloated interfaces that contain methods they don't actually need. We take our massive bank operations module and break it down into smaller, specific operational protocols so that each part of the system only interacts with the tools it requires. Dependency inversion ensures high-level logic remains independent of low-level tools. By connecting our bank to an abstract database interface instead of a specific SQL database, we can change storage technology in the future without rewriting core logic. Applying solid principles transforms rigid code into a modular ecosystem that supports significant, predictable growth. Consider a scenario where multiple ATMs attempt to update the same central ledger simultaneously. This causes massive data collisions, corrupting the entire financial record. To solve this, we use design patterns, standardized architectural solutions developed to address recurring vulnerabilities in software systems. We will implement the singleton pattern, which ensures that a specific class can only have one active instance in the system at any given time. By wrapping our bank ledger in a singleton metaclass, we physically prevent the system from creating duplicate, conflicting ledger objects. When we test 3 simultaneous ledger requests, the system routes them all to the same memory address, maintaining a single, consistent source of truth. Design patterns provide standardized solutions that preserve system integrity in environments where basic logic might otherwise fail. What began as a series of empty files is now a professional banking architecture. Our encapsulated classes, modular interfaces, and protective patterns are now working in harmony. By establishing these controls over state and behavior, you have moved beyond simple coding and into the realm of system engineering. You can apply this same framework to an e-commerce platform, using encapsulation for secure carts and abstract patterns to manage varying inventory systems. Mastering these strict boundaries and structural contracts is the fundamental language of large-scale system architecture.